calculating reaction-free energy under non-standard conditions. So essentially, this is getting to us to use the standard Gibbs free energy and then attenuate that for the actual concentrations that we have. So how to calculate the reaction-free energy under non-standard conditions. So you can calculate the standard reaction-free energy from our Gibbs free energy of formation for all our reactants and products. If we're under non-standard conditions, usually this is going to mean a different temperature or different concentrations of reactants and products than we would have it under standard conditions. So the equation we're using is delta G under non-standard conditions, so it's going to lose the little degree symbol. It's related to delta G under standard conditions, and we add the term plus RT ln Q. And what is Q, you may ask? Well, you may remember. Q is going to be the reaction quotient, which is when we substitute in the equilibrium constant expression when we substitute in non-equilibrium values. So basically like other concentrations, right? So we're looking at something a little bit like this. So because we haven't actually been given the standard Gibbs free energy of formation, we are going to have to calculate that. And then we're going to have to calculate our reaction quotient Q. Everything else should fall into place. So first of all, calculating our Gibbs free energy of formation. So I'm just going to look up those Gibbs free energy of formations for each of our reactants and products. So minus 3884.7. And that's going to be kilojoules per mole. That is for our calcium phosphate. For our calcium, it's minus 553.6 kilojoules per mole. And for the phosphate, it is minus 1018. 0.7 kilojoules per mole. So we're just going to do a real quick calculation of delta G of formation for this reaction based on these. Sorry, I couldn't make them sync up any better, but there we go. That's approximate. So again, it's going to be the sum of all the delta G formation for our products minus the sum of all the delta G of formation for our reactants, and that will give us our standard Gibbs free energy of formation for our reaction. Gibbs free energy of formation of products minus Gibbs free energy of formation of reactants. Okay. Make that fit on one line. Yes, please. So there's my delta G. And this is standard. And let me just do my ugly sigmas first. And again, be careful with these. Use parentheses, etc., to make sure we get the sign right. Standard. Okay, so summing up for all our products then, let's see, we've got 3 moles of calcium, so 3 moles of calcium ions times minus 553.6 kilojoules per mole, plus how many moles of phosphate? We've got 2 moles of phosphate times minus 1018.7 kilojoules per mole. Add those together and then subtract from that just the calcium phosphate's the product, so sorry, reactant, and there's only 1 mole of that times minus 3884.7 kilojoules per mole. What's that going to come out to be then? Well, let's see. Get calculated. That is going to equal plus 186.5 kilojoules, right? So remember that's my delta G of reaction under standard conditions. If I can draw that real quick. So just remember that's standard. My little delta, make it as pretty as I can. It could be worse. All right, so now we need to write our equilibrium constant expression, or reaction quotient Q, is going to be equal to the concentration of calcium 2 plus, and that will be cubed, because there are 3 moles of calcium in the equation, times the concentration of the phosphate ion, PO43 minus, and that is going to be raised to the power of 2 moles. Divide through by the reactants, but the reactant, the calcium phosphate, is in the solid state. So we're just going to ignore that. because remember, heterogeneous equilibrium rules, we're only going to count something that has a concentration. So either aqueous solution or partial pressure of a gas is all that's going to count into the equilibrium constant expression. So phosphate has got a concentration of 0.501 molarity, and that will be did I say phosphate? No, I meant to do calcium first. Calcium, let's keep it the same, 0.192 concentration raised to the power of 3 times the concentration of phosphate, which is 0.501 raised to the power of 2. That's just going to be a number. It's going to be 0.001776. That's probably going to be enough decimal places. All right, so now we can substitute into this delta G under non-standard conditions equals delta G under standard conditions plus RT ln Q. Okay, so R is just the gas constant, T is the temperature, 25 degrees Celsius, so 25 plus 273.15 is 298.15. So don't forget to convert your temperature into kelvins after all that effort, right? So delta G, oh, I can't make this pretty, is delta G standard plus RT ln Q. So let's stick it in. So delta G standard we just calculated is 186.5 kilojoules. Now I know the R in RT ln Q is in joules per mole per Kelvin, so you got to convert one or the other. So 1,000 joules or 10 to the 3 joules over 1 kilojoule will convert that delta G standard into joules, just for ease of units, right? So that's the first bit, plus RT ln Q, so plus R, 8.314 joules per mole per Kelvin. And then obviously our temperature is going to come in next. So times 298.15 Kelvin times the natural log 0.00177766. So basically you're going to have whatever your gives free energy of formation under standard conditions, and this is the term you're going to add to it to attenuate that for being under non-standard conditions. And whatever I'm going to get out of here is going to come out in joules, joules per mole. So I get 170,800-ish joules per mole, and obviously, maybe not so obviously, usually we would give delta G in kilojoules per mole, so I'm going to have to convert that to kilojoules per mole. So it's 1,000, so 1 kilojoule is I haven't got room to do this. 1 kilojoule is 1,000 joules. So I'll go quickly just stuff in that unit conversion. Yeah, I know I just converted into joules, but I had to get it to cancel out somehow. And so that's going to be about 171 kilojoules per mole would be my answer for that one. All right, so that's all you need to do there.